to talk about two problems that seem contradictory, but I'm going to argue are intimately related to one another. So the first problem is that people are still smarter than machines. This is not necessarily a problem for people, it's more of a problem for machines. So despite the recent advances in AI, you can point to lots of individual things that people can still do better than computers can. But more generally, you only have one system which is capable of doing all of those different kinds of things, and that system is human beings. So the current trend in machine learning is one of solving problems by increasing the amount of data and the amount of computation that get thrown at them. So if I was showing slides here, I'd show you a nice picture which some of the people at OpenAI made, where they took a bunch of the recent sort of milestones in AI, starting from ImageNet classification through things like AlphaGo and AlphaZero. They took those cases, they plotted out as a function of time how much compute went into each of those things, and you see there's a nice increasing line. And I would argue that, in fact, focusing on that trajectory is something which isn't necessarily going to take us in the direction of getting systems that can do the kinds of things that people can do, in particular, this kind of generality that characterizes human intelligence. So going back to a more historical example, if we go back to something like the interaction between Deep Blue and Garry Kasparov, something which has been taken as a sort of evidence for the success of AI, you can actually look at that case as something which instead reveals something important about the power of human cognition. So, while Deep Blue, won the majority of those games, they were doing it under entirely different conditions, where, Kasparov was playing with, as somebody mentioned, the energy equivalent of a light bulb, and being able to evaluate, maybe like 3 different moves a second, whereas Deep Blue was playing with, a huge amount of energy resources going into it, and the capacity to evaluate something like 100,000 moves per second. So the critical difference there is that I think one of the things that helps to make human beings intelligent in the way that human beings are intelligent is intrinsically the fact that we have limited cognitive resources. And it's our ability to efficiently manage and use and deploy those cognitive resources in different ways to engage with the different kinds of computational problems that we encounter. That's part of what makes us intelligent in the way that we characteristically think of as intelligent. So if we're doing slogans like Alison was doing, I think the slogan here would be humans, doing more with less, right? And that kind of perspective is not necessarily one which is encouraged in the current sort of machine learning-based approach to AI, but I think is going to be critical to being able to succeed in sort of getting past some of the challenges that the field is currently facing. The second problem, which, again, as I said, seems at odds with this, is that people are not so smart, right? So on the one hand, we have people smarter than machines. On the other hand, we have people having a reputation for being kind of dumb, right? And you have heard hints about this reputation. I think Ian said, people have well-known cognitive defects, right? Danny Kahneman is one of the people who really helped to reveal those defects. The way in which those defects are typically characterized is in terms of a comparison of human beings against a kind of classical notion of rationality, right? And this classical notion of rationality, I think, isn't actually a good criterion for evaluating human behavior against, or importantly, the behavior of machines. So this classical notion of rationality is one that says that, in any situation, what you should be doing is taking the action that maximizes your expected utility without regard for how hard it is to compute that action. And so that kind of characterization of rational behavior is something which is not achievable by any realistic organism, whether it be a human being or a computer, because all realistic organisms are limited in the amount of computation which they have available to them. And so the reason why this is something which sort of matters in the context of both AI and understanding human cognition is that it suggests that maybe there's a different way that we could go about characterizing what constitutes rational behavior for realistic entities. And it might be one that gives us different insight into actually understanding the ways in which human beings behave and whether or not the things that we do actually constitute cognitive defects. Part of the reason why that's important for AI is not just because that's a criterion that we're going to hold AI systems to, but because if it gives us a model of human behavior that has the same kind of generality as that classic notion of rationality, then it gives us an important tool that AI systems are going to need to have in order to be able to act in ways that are beneficial to humans, which is it gives us a component of a system which is going to be able to make inferences about what it is that human beings want based on the ways in which human beings behave. Right? So if we imagine a super intelligent system which has far more computational resources than us mere humans, that's trying to make inferences about what it is that the humans that are surrounding it, which it thinks of as cute little pets, are trying to achieve and so that such that that system is able to act in a way which is consistent with what those human beings, remember that's us, might want, then that system needs to be able to simulate what it is that an agent with greater constraints on its cognitive resources should be doing, right? And should be able to make inferences like the fact that we're not able to, calculate the zeros of the Riemann zeta function or, prove or discover a cure for cancer doesn't mean that we're not interested in those things. That's just a kind of consequence of the cognitive limitations that we have. And to tie it back to Alison's presentation, as a parent of two small children, right, this is a problem that I face all the time, which is trying to figure out what it is exactly that my kids want, kids who are operating in an entirely different sort of mode of computation and with, having to build a kind of internal model of how it is that a toddler's mind works, such that it's possible to unravel that and go backwards and work out that, there's a particular motivation for the very strange pattern of actions that they're taking. So both from the perspective of understanding human cognition and from the perspective of being able to build AI systems that can understand human cognition, it's desirable for us to actually have a better model of how it is that rational agents should act if those rational agents have limited cognitive resources. Okay. So that's something that I've been working on for the last few years. And we have a kind of approach to thinking about this that we call resource rationality. And this is closely related to similar ideas that have been proposed in the artificial intelligence literature. One of these ideas is the notion of bounded optimality, proposed by Stuart Russell. But basically, what we want to do is to say, let's come up with a criterion that describes how it is that a rational agent, be it a human or computer with limited computational resources, should use those computational resources and then act. And you can think about this as characterizing basically a kind of optimization problem similar to the classical optimization problem, which says, well, what you want to do is maximize your expected utility. Now we're going to think about how we should go about maximizing, so how we're going to go about choosing an algorithm which is going to lead to an action that we take, such that that algorithm is maximizing expected utility while minimizing the associated computational costs, right? And so if you have a sort of model of the computations that are available to an agent, the costs that are associated with those computations in terms of an amount of time that they take or an amount of other kinds of resources, then you can define an optimization problem which then gives us a way of saying what constitutes rational behavior. Rational behavior is no longer the agent who always takes the perfect action in the perfect circumstance. It's the agent who follows the algorithm that leads them to take the action that best optimizes this joint criterion of maximizing expected utility while minimizing computational cost. So what I want to do is give you one concrete example of a way in which that's sort of useful perhaps in understanding one of these classic cases where people behave irrationally. And that example is what's known as the availability heuristic, and in particular the overrepresentation of extreme events. So one way in which people often act irrationally with respect to a kind of classical criterion is that if you ask them to estimate the probability of something like a terrorist attack or a shark attack or these other sort of extreme, negative circumstances, they significantly overestimate those probabilities, right? So when you're getting on a plane, you're spending more time than you should thinking about the possibility that the plane will crash. When you're going to make a decision about going snorkeling, you're thinking not enough about the, tiny worms on the corner of the coral reef, and far too much about the sharks, which are very unlikely to bite you. And those things seem irrational, right? There are things that are going to affect your behavior in ways that aren't necessarily, consistent with the way in which a purely unbiased agent who's appropriately evaluating expected utilities might act. Well, when we put that in the context of a kind of resource rationality framework, we need to define the computational problem that we want to solve, talk about the resources we have available, and then think about what's the best kind of strategy for deploying those resources. And in this context, it's clear that what we want to do is evaluate something like an expected utility, right? That requires summing over all of the possible outcomes of our action, the utility of that outcome multiplied by its probability. That's potentially a costly procedure, right? When you're taking an action in the real world, there are many, many possible outcomes, and they're going to have a variety of different utilities. So let's say that you're going to try and approximate that calculation, and the way you're going to try and approximate it is by drawing samples, doing a Monte Carlo approximation. You're going to sample some possible outcomes, and then you're going to consider the utilities of those possible outcomes and add those up, and that's going to be the way in which you're going to evaluate whether you should take that action. And the choice that you have to make is a choice about what distribution you're going to sample from. So your goal is to choose a distribution such that you're able to draw a relatively small number of samples, because those samples are costly. That's time you're spending, standing around rather than going snorkeling, right? And you want to choose basically come up with a way of drawing those samples which is going to allow you to minimize those costs. Make decisions quickly, make decisions with small numbers of samples. So when we think about trying to do an approximation via this sort of Monte Carlo procedure, the intuitive, simple, basic, straightforward thing people think of is, what about sampling directly from the distribution that you care about? So you're going to think about possible outcomes, but you're going to think about them with the probabilities that are associated with those outcomes, right? So you sample from that distribution that has the benefit that it gives you an unbiased estimate of the probabilities. But if you're in a situation where there's an extreme distribution, like a sort of very skewed distribution of possible utilities, and where there are low probability events that have extreme negative utility, say, that's a strategy which actually doesn't work very well. And the reason why is that the estimate that you end up getting is one that has a huge amount of variance, right? So from one set of samples to another, there can be a very big difference in the value that you get, because you may or may not have included those extreme events. And so you can ask another question now. If we're dealing with small samples, it's not the bias in the estimate that's going to be the problem. It's literally the variance in the estimate which is going to end up killing us, right? So if you were going to say, try and make a decision about whether you should play a game of Russian roulette, right? There's a revolver in front of you. It has six bullets, six spaces for bullets, one of which is actually a bullet. You can calculate how many samples you need to draw in order to be 99.9% sure that you should not play this game. And it's something like 51 samples, right? There's a lot of variability there. You really want to be able to make that decision much more quickly. And so you can ask, what's the distribution from which we should sample in order to minimize that variance? And there's a nice result which says that that distribution is one which is proportional to the probability of an event occurring multiplied by the absolute value of the utility of that outcome. And this results in a biased estimate. It's biased in the direction that it's going to overestimate the probability of extreme events, but it's the estimate that reduces variance. And so if you're trying to do the least computation you can do while minimizing the chance that you end up accidentally killing yourself, this turns out to be the best strategy. It's a resource rational strategy. And so this is an example of a case where we can take a classic way in which people,
I was just trying to parse that equation in my mind.
Right.
Instead of sampling according to the probability, you sample according to the probability weighted by
proportional to the probability multiplied by the absolute value of the utility.
You don't know how to sample that.
You don't know how to sample that. I can tell you how your brain can do it for you, though.
All right.
So what you do is you wander around the world, you encounter events, and you remember those events as you encounter them. But the probability that you remember them, or the probability that you retrieve them from memory, is proportional to the absolute value of their utility. Yeah. So Herb Simon talked about this idea of bounded rationality, but he was very reluctant to define what bounded rationality meant. And in fact, there's a letter that he wrote to Gerd Gigerenzer where he makes it very clear that ambiguity was a feature, not a bug. That it was really intended to make people just think about alternatives. And so the way that I think about it is that the notion of boundedness picks out a subset of the space of possible strategies that you can follow, right? That's sort of the optimal strategy. That's one particular thing. That's the thing that's picked out by the classical notion of rationality. Bounded rationality says you don't have the resources to get there, so now there's a space of alternatives. And then bounded optimality says out of that space, you're going to be choosing the thing which is going to be the best thing. And so what it does is it gives you back that optimization criterion that gives you a way of then having a theory of behavior which has the generality of that classical notion of rational behavior.
Couldn't you also just a little bit switch the criteria or the definition of best?
So best, yeah, subject to that joint optimization problem. Yeah, that's right. Yeah. Okay, so so the point of this example, though, is that this is a case where it seems irrational under a classical notion of rationality, but it makes sense under, I think, what's a more realistic characterization of what rational behavior might be like. And thinking about, there are other cases that we've worked through where we can show that some of these classic heuristics fall out of this kind of approach. And while heuristics result in biases, being biased doesn't mean that you're not doing the thing which is resource rational. Bias is a natural trade-off to accept in order to allow you to operate with limited cognitive resources. So just because you see biased behavior, it doesn't mean that people aren't doing something that makes sense. It might mean that people are doing something that makes sense, but they're operating under resource constraints. The way that this ties back to some of these questions about machine learning that I started out with is that the immediate question that should come up for you is, if people are following these kind of resource rational strategies, how are they discovering them, right? How are we ending up finding good ways of using the limited cognitive resources that we have? And this is a problem that's called rational meta-reasoning, right? How do we rationally reason about the strategies that we should be following as agents in terms of the computational resources that we deploy for solving particular problems? So we're not just reasoning, we're reasoning about the way in which we should reason. And it's, again, something where I think you can do a little bit of work and actually get a lot of leverage. And so one way of thinking about this, there are a couple kinds of problems of rational meta-reasoning. One is a problem that we call algorithm selection. This is a case where you know what the algorithms are and you're trying to choose between them. But the more interesting case is what we call algorithm discovery, where your goal is to come up with the right algorithm to use to solve a particular problem, putting together these pieces of computation that you're going to use to solve that problem. And the way that you can approach this is by recognizing that, in fact, this deployment of an algorithm is itself a decision problem. It's a sequential decision problem where you're making a decision about the sequence of computations that you're going to execute, one after another. And framing it in those terms allows us to tie it back to classical problems that are faced in decision-making, reinforcement learning. You can characterize the problem of selecting what computation to perform through this process as a Markov decision process, which is something that we can solve using these classical tools. One of the ways in which most machine learning methods work at the moment is you take a single monolithic neural network and you throw it at your problem. But that's different from the way in which I think we've been characterizing human cognition as working, which is that you've got the pieces of these computations, you're deciding how to put these together to solve different problems. And in a neural network world, that's about constructing what they call a computation graph, right? The sort of the sequence of transformations that you're applying in order to get to a solution. So you can formulate the problem of constructing the right neural network to use to solve a particular problem as a decision problem in these same terms. And it's a decision problem about the computations that you deploy in order to solve a problem in the world. And so I think using these kinds of tools together with engaging with a set of problems which is much broader than the canonical approaches that are currently being taken in machine learning, that is, not just training a system to play chess or to learn an aspect of language or to do motor control, but trying to train the same system to find the right cognitive modules to put together in order to solve all of these different problems, gives us a path beyond the current sort of monolithic approach to building these sorts of machine learning systems, and maybe a path towards building more human-like AI systems.
Question vis-a-vis the claims made by the deep learning community. Where is this going? Is it going into human intelligence? Is this going to be AI that we can use, or is it going to simulate human? When you talk about the next revolution.
Yeah, I mean, here I'm focused on what I see as the gap between what people do and what current approaches in machine learning do, right? And whether you want to close that gap is going to depend on what your motives are, right? If you just want to build the best image classification system, then you don't have to care about this. But But if you want to build a system which is doing a wide range of tasks in the same sort of general way that humans do, then there's the kinds of architectural questions that you want to engage with.
Maybe you want to rule this one out. But how would you deal with how would you deal with the idea that humans eat too much sugar and fat? We know evolutionary reasons why. We know, and the human is told that that's not optimal for your health, and they do it anyway. It's not that an example. It seems is not a question of limited calculation resources.
Right.
So maybe it's not the area you want to study.
Right. So
it is a suboptimal behavior.
Right. No, and I'm not claiming that all instances of suboptimal behavior are explained in this way, but I think a subset of them are. The other thing that I'd say, though, is that adopting this perspective changes the way that you should think about debiasing. Right? So classical approaches to debiasing, which is trying to make people act in ways that are more rational, say something like, people are following the wrong strategy here, let's teach them the right strategy and see, and improve their behavior. But from my perspective, that's not going to work because the strategy that people are following might actually be a good strategy given the resources that are available to them. And so instead of focusing on modifying people's strategies, what you do is focus on modifying the structure of the environment around them.
You can also modify their resources. For example, if you teach them calculus, they can think about rates of change in a way that somebody that is naive cannot.
Yeah, so you can change the cognitive, the set of computations that they're able to perform, and as a consequence, that can change the strategies they perform.
One thing that strikes me is that we often, when you were talking about the bounded rationality, however it's defined, roughly speaking, using the definition that you very plausibly invoke, is that we often assume that if we don't have the resources to sample very widely, we're making poorer decisions than we would have had if we could have sampled more widely, but we understand it because in that circumstance we didn't have access. So being scared of a shark attack, we don't have that information, so we would have realized there are only a handful of shark attacks in 10 years. But it could be the case. Recently, some of my nearest and dearest went swimming at the beach near where we live, where there was a shark attack 2 days before, and there's seals swimming there.
Right.
So,
The sharks that aren't eaten. It was fine. It was totally
so
fine.
they didn't know.
There's more seals, so there's going to be more sharks.
They didn't know the broader, but the conditional probability
Was elevated.
was elevated partly because there was a bound on access to information. So sometimes it seems to me the conditional rationality, the bounded rationality could actually be better than the universal knowledge because it might include conditional probabilities that were specific to the circumstance.
Yep.
So, it may be that people are not only being rational when they make these local decisions because their knowledge of the broader universe of data is limited. It may also be because they see something. They add factors that are relevant or that they suspect might be relevant to their decisions that would actually make it quite sensible, not just sensible sub specie, the bounded.
Yeah, so I can give you an interesting example like this, which is we looked at a case which is you're basically doing planning, you're doing decision making over some horizon, but we assume that your horizon is limited relative to the problem you want to solve. So say you're making decisions about a 20-year trajectory in terms of your career, but you're only able to see plan out into the future 5 years or something like that. So under those circumstances, it turns out that it's beneficial to be optimistic. So it's beneficial to conflate your utility and probability in exactly the way that I'm talking about, where you overestimate the probability in this case of good events, right? And it's beneficial to be optimistic because if you were only able to plan over that limited horizon and you were being perfectly calibrated to what the probabilities of events are, you miss the chance to pursue a low probability outcome, which has a big payoff in terms of the 15 years beyond the part which you're able to see to. Whereas if you're optimistic, you sort of erroneously pursue those attractive career opportunities that you're going to fail at, but the fact that you pursued them put you in the position to be able to then benefit from those in the future.
So I'm a little confused about what you mean by sampling here. I never actually quite understood what people mean by sampling. If you mean
look at my past history and count the number of times I was attacked by a shark, right, then I estimate the probability to be 0.
Right.
Well, that's clearly wrong because you know that people are attacked by sharks, but your information is just, I read in the newspaper that somebody was attacked by sharks. So what do you mean by sampling? I'm still trying to, I think Bob and I are still confused about this, this biasing by the absolute value of utility.
Okay, so when we talk about sampling as a cognitive mechanism, we're pretty agnostic about what the distributions are that you have access to.
Well, what do you actually mean by sampling? I mean, do you mean I am drawing from a set of events with this distribution?
Yeah.
But how do you draw from that if you're thinking about shark attacks?
So I think the best example of this is, as I was saying, like cases where you are able to somehow generate samples from memory as a consequence of your experience, plus, as you were saying, the testimony of others and the things that you've read about, and you're sort of putting all of those together into a distribution that you're then generating samples from when you're considering outcomes.
Is this just simply a formalized version of Kahneman's thinking fast, thinking slow?
So what I would say is that what psychology has done very well, and Kahneman's work is a good example of this, is characterizing a wide range of circumstances where people behave in ways that deviate from this classical notion of rationality. What psychology has not done particularly well is developing a formal theory with the same generality as that classical theory of rationality that actually explains, in particular circumstances, how people are going to act, right? So
your answer is yes.
my answer is that it would be very nice if we were able to formally express those things, right? And that's the kind of goal that we have in mind. Yeah.
So it's sort of doing prospect theory right?
Well, more than prospect theory, right? Prospect theory.
But I mean, the point is, the prospect theory was supposed to be, here's the positive theory that's the counterbalance to the...
So prospect theory is still a descriptive theory.
Right.
It says people are making decisions using this function to characterize probabilities, this function to characterize utilities. Those are empirically derived functions, right? So the kind of thing that you'd want to be able to do is to say, we can derive from this why people are taking actions in this particular way. And I'll say that the method I talked about, that sampling-based method, that actually predicts people's decisions in an empirical choice prediction setting better than prospect theory does. So that's just starting from first principles and deriving the solution to the
Have you written something that you could send
Yeah,
us?
I can send it.
Please.
But I have a different question, which is, it is true that this gives you a good explanation of why people are acting the way they do, but another respect in which people seem to be superior to AIs gets back to this point about getting veridical representations of what's going on in the world around us, notably in science. And it doesn't seem, on the face of it, as if having limited computational bounds would be a bit, I mean, it could be, it's an interesting thought. Is that bug of having limited computational bounds actually a feature when it comes to abstracting the structure of the world around us?
So I think it's a feature because it forces us to be good at this kind of metacognition, right? And so if you think about the kinds of things that AI systems currently struggle with, one of these examples is being able to find reasonable sub-goals in a reinforcement learning task, right? There's, if you look at the set of computer games that AI systems can play better than people, and then you look at the ones where they fail, the ones where they fail are ones where you have to formulate some kind of abstract goal, like I'm going to get the key so I can open the door, which is going to appear in 2 screens, and so on. But the human ability to do that is entirely a consequence of the fact that we have limited computation. If you're able to see an arbitrary distance into the future, you don't need to formulate sub-goals. You just follow the optimal policy. It doesn't need any sort of decomposition to do that. Decomposing the problem in that way is what you do when you try and solve it with less computation, right? And
so you get more generality as a result of that?
Being able to form those abstractions allows you to represent the problem in a way where you're able to solve it, even though you're only able to consider 3 moves a second. Right?
Are you saying what seems like cognitive defects are actually useful features because we're all descended from people who weren't eaten by sharks? We must be getting something right.
So I'd say what seem like cognitive defects are defects in the sense that they're a consequence of the limitations that we operate under. But the fact that we operate under limitations means that we've had to develop a kind of cognition which is not well represented in current AI systems, which is being able to reason about how to use the bit of smarts that we've got to solve a wide range of problems.
There's something interestingly parallel with Alison's talk of a push to humanize AI, as it were, to get them to do something more like what we do, if they're going to live among us, as it were.
Yeah, so that's another problem, right? Which is, I think it's less important that, so it's important that we have a theory of how they work in order for us to interact with them, but it's even more important that they have a theory of how we work in order for them to interact with us.
They need a theory of mind.
They need a theory of, not just a theory of mind, but a theory of, like, so human theory of mind is actually one of the sort of the surprising things that we've discovered is that expected utility theory is a terrible model of how people actually act, but it's a really good model of how people think other people are going to act, right? So we have a kind of theory of mind. Our theory of mind is flawed in that we think that people are more rational than they are. So if you wanted to make a machine that could actually reason well about how to interpret human actions, it would be nice if we were able to do so in a way that took into account cognitive limitations as well.
I mean, sorry, could we just pursue this to the end? In the model of my Adam, he understands humans by reading world literature. And since he's got a very good memory, the totality of world literature, imaginative literature, is not a prescription, but a description of what humans are. It doesn't necessarily provide solutions. It just takes us through all the moral corners that people have been able to imagine.
Yeah, and that's not a bad approach in terms of, that's pretty consistent with the way that current machine learning methods work, which is that you drown them in a huge amount of data and they're able to memorize the relevant aspects of the data and generalize a little bit, right? But not necessarily forming a systematic theory that they're able to use to generalize to new circumstances.
But I think there's reasons why his reading world literature, as opposed to just taking in all the things that are in the papers, might actually be an advantage. Which is, if you think about trying to see what the boundary cases are, right? So you're trying to figure out the structure of a particular theory, for example. You're trying to figure out what the consequences of it are. You're often better off thinking about non-existent boundary cases than you are thinking about the things that you actually see all the time. So if you think about, Einstein trying to explain his theory, if he just said, well, look, here's a prediction of the theory, if you drop this, it will fall at this particular speed, according to my theory, that would not be very informative. And actually having these fictional boundary cases seems to be a better way of telling you, here's the big important differences between my theory and other theories. So if you're thinking about human beings, for instance, it might be that having these fictional extreme boundary cases, which is what you typically find in world literature, is actually a better way of knowing what people's psychological structure is, or at least what people's theory of their own psychological structure is, than it would be if you just looked at all the things that were in the newspapers.
The sum of all the things that didn't happen is near infinite. I mean, the possibility for world literature as a space, a mental space, is
Not near it, it's infinite.
May I also say that actually in terms of, this is speaking from my experience teaching numerical methods and probabilities to undergraduate mechanical engineers, which is what they learn, and this is actually what a lot of statistics and sampling theory learns, is that we sample from something, everything obeys the central limit theorem, the deviations are in a Gaussian, and so, hey, a Six Sigma event, like in Six Sigma management, Six Sigma means it has a probability of 1 in 10 to the 12th of occurring. But, from experience, we know that actually distributions have fat tails. They are power laws. They are log normal distributions, and Six Sigma events occur all the time. And, if you design a bridge thinking everything is just a Gaussian distribution and Six Sigma is never going to occur, then you're going to have bridges that are falling down right and left. And that's probably also, so I'm actually just agreeing with you that, the fact that shark attacks occur, even though they're extremely rare, means you probably want to give it some thought that it might happen.
So it seems to me like this notion of bounded computation is also relevant to the discussion early in the morning of Allison's point about the complexity of goals and, in some sense, the unsolvability of goals. So I'm actually very bad at predicting what's going to make me happy or not sad. So I have goals instead. And what goals are is they're basically admissions of failure of my ability to make that computation. So instead, what I try to do is act in a way toward going to something else that's kind of a surrogate for that. It's kind of a stand-in for that. And in the same way with machines, when I give machines goals, that's really, you know, I can't really decide what's going to make me happy for the machine to do. So what I'm doing is I'm putting in a kind of, I'm using my bounded rationality and establishing, you know, a goal, a stand-in for that, of what made me happy for the machine.
Yeah. I mean, so we've been thinking about ways of helping bounded humans do a better job of achieving their goals if they're able to specify what they are. And it's actually based on reversing that loop. So instead of having humans define the reward functions for machines, what you do is you have machines define the reward functions for humans. And so we have an approach which is called optimal gamification, where basically the idea is if you have a problem that you want to solve that's a sequential decision problem, and you know we can write it down, but you're not able to sort of see far enough into the future to actually work out what the optimal policy is, you can take that and give it to a computer, get the computer to solve that problem, and then we can take the solution that's computed by the computer and use that to construct a modified reward function for humans, such that even perfectly myopic humans following the modified reward function will achieve their long-term goals. And we actually have deployed this system and shown that we can reduce people's procrastination. So procrastination being a classic example where you've got a big payoff that's far into the future, and then the optimal modification of that reward function makes that long-term payoff smaller, but spreads it out back through the, through time, so that you can follow the breadcrumbs and then eventually get there.
So this also suggests a modification of the voting algorithm Stephen suggested earlier, which is the real great democracy would not be the one where you submitted an algorithm showing what your preferences were, but merely you submitted an algorithm that showed what would actually make you happy. And then you take the voting commission takes all of those algorithms, runs them under different scenarios, and picks the optimal.
So I would caution about the 3 moves per second being misleading in that if you view that as an update rate, it's updating a very, very, very high-dimensional feature vector, unlike the move generator you're comparing in Deep Blue. And so if you look at high-dimensional optimization algorithms, the effective operations per cycle is a huge number because you're moving this giant feature vector, and the 3 moves per second is the velocity of this high-dimensional feature vector, which is way more than 3 moves a second.
I thought you were going to say, I would caution against amending the Constitution to have the result of the presidential election be decided by an artificial intelligence.
Yeah, it's often misinterpreted by a simple computing model.
We did already.
Thank you, John.